Alright, so this video here is purely just another example of doing maximum power transfer for a slightly more complicated, complicated circuit. So we have two questions here. The first question is what should RL be for maximum power transfer, and the second question is what is the maximum power delivered to RL. Now, if you did the optional readings, on Thevenin equivalent, Thevenin and Norton equivalents, you could use those analysis techniques. In other words, what I'm trying to emphasize here is that there are some optional readings that I have in the course, and again, the optional readings are not required. You won't be tested over the material in the optional readings, but the optional readings provide you some further insight into some further circuit analysis techniques. They're typically more advanced techniques, and are ones that, while they're very important, aren't necessarily required for to make sure we have a good fundamental understanding of how circuits work. So that's why we don't cover them in this course. But I always like to have them as optional for those people that do want to read about those techniques. Alright, so what we need to do here is we're going to first find RL for maximum power transfer. I'll even label these part A and part B here. So for part A, we just have to find Req. Now what I'm going to do here is I'm going to draw the circuit here with some of the things here. So this 4 amp, this is a current source, so this becomes an open circuit. So I'd have basically a wire here and a wire here coming to this 1K ohm resistor, and then voltage sources become short circuits, so that 2 volt would become a wire, and then I'd still have that 2 kilo ohm resistor. That 3 volt power supply would become a short circuit, so it'd be a wire. And so this is then what RL would be. Now, because we're looking in from this side here, from what the load is seeing, we can say, well, these wires are open circuits, there's nothing connected to them, so I can actually just get rid of those as well, because there's nothing connected to it. When that current source was turned off, it became an open circuit, so there's no current that can go through there, so there's no need to draw those two branches there. Alright, but then we can see here, actually once we reduce it here, this is a very simple circuit to do series and parallel combinations of. In fact, it's not even really anything at all. We simply have a 1K in parallel with a 2K ohm, which I'll just use our short formula, so 1K times 2K over 1K plus 2K. So this would be 2/3 kilo ohm, which I will just go ahead and write as 667 ohms. I know that's rounding. So 667 ohms. That is our equivalent resistance. So then for part A, we would set RL equal to 667 ohms for max power transfer. Okay, so for part B here, we're going to need to analyze this circuit. So I'm just going to lasso this circuit here. And just a second here, I'm going to copy and paste that. And just move down here. Close that. I don't want that. I didn't copy and paste. Copy. Oh, there it is, but it's not exactly in a great spot, so let me move that over. Would have been easier if I just redrew the circuit, right? Okay, that's close enough here. So this is the original circuit, but now we know that instead of having RL here, I will go ahead and put this in 667 ohms. Now, as I said, if you had done the optional readings at this point, you'd have a much simpler circuit, but you would have had to do a lot more work at the beginning to find the Thevenin equivalent. So really, it's kind of, do you want to do the work at the beginning or do you want to do it at the end? And here I'm just going to do it at the end here, where you need to find then the power across the 667 ohm resistor, because we're looking for what power is being dissipated. Well, we could look at doing maybe nodal, but if I look here, how many nodes do I have? I've got 1, 2, I've got 3, I've got 4 nodes. Now one of them would be set to ground, but that would mean that I would have 3 other ones, and actually I've got some difficulty here because I've got a node here where it's like, oh wait, there's 2 volts here. So if I try to do this voltage minus this voltage, there's no resistance there. So that's actually going to make things a little bit more difficult for us. There's ways you could go about doing that, but they're a little bit more challenging. So what we're going to look at here instead is like, well, wait a minute, let's maybe try and do some loops. So I'm going to draw a loop here. I'm just going to label this I1. And the reason I'm going to do this one as I1 is because I'm going to go ahead and then know that I1 is the current through that 667 ohm resistor, and then the power being delivered would be I squared times that resistance. Now, I'm going to draw this loop, I2, in the same direction. I typically draw them clockwise. But then here, on this loop here, I'm actually going to draw this one in counterclockwise. And I'm going to do this counterclockwise on purpose because if I look at this loop here, I've got a current source. And it's this current source is the only thing touching this loop here, at least on this side here. So, no, I don't want to type anything. So that means here that we know right away that I3 is equal to 4 amps, which is great. We've got I3 is equal to 4 amps. So really I only have 2 unknowns. I've got I1 and I2. So let's go ahead and write some loops here. So let's do a loop for I1. You can start anywhere. Well, first off, notice that it's hitting the positive side of this 3-volt voltage supply. If I draw the arrow, if I continue this arrow, the arrow hits the positive side of that 3 volt. So I'd have, I'll even emphasize, plus 3 volts plus 667 times I1 plus now 2K. There's 2 loops hitting this 2K ohm resistor. So it'd be 2, and I'm going to write this as 2000 since I'm doing 667. And this would be, well, the primary loop is I1. And then, of course, we notice that I2 is going in the opposite direction of I1. So this would be minus I2. And then to finish it up, we have to include that 2-volt power supply. So, but I'm coming in on the negative side, so this would be minus 2. And then this is equal to 0. So this is my loop 1 equation here. So let's combine some terms here. I'm going to multiply things out. I'm going to skip some of the algebra steps here. So we'd have 2,667 I1 minus 2,000 I2, and that this is going to be equal to -1, because you'd have 3 minus 2, which is +1, and then I'd move it to the other side. So that's my loop 1. And then I'll go ahead and do loop 2. I'll go ahead and just change colors here for fun. Loop I2. And now this one's a very small loop here. There's only 3 components that we have to go through. And, you know, just for no other reason, I'll start at the 2-volt power supply. So I got 2 volts, because it's coming in on the positive side, plus then 2 kilo ohms, which, since I wrote out the previous line in ohms, I'm going to do the same thing here. Technically, you could leave it as kilo ohms, but I like to make sure all of my units match so that my answers match and my units on my answers are correct here. Because you can get into trouble here with units on your answer if you don't keep your units consistent. And so it'd be 2000. Now again, the loop we're in is what we take as positive, so I2. And then of course I1 is going in the opposite direction, so minus I1. And then we have a 1 kilo ohm resistor. Now, thing you have to be careful with is, again, this is not just I2. I2, of course, is definitely in the positive direction because we're in the loop I2. But then if I notice here, I've got I2 going up, and then I3, which is also going up through that 1 kilo ohm resistor. But we know what I3 is. It's 4 amps. So we have minus 4 equals 0. And so simplifying this equation, we'd have minus 2000 I2, I1, plus 3000 I2, and then if we're careful here, this is technically, I mean, it's almost minus 4000 here, but we got this plus 2 here. So this is really going to be equaling 3998 on the right hand side, because we've got this 2 here that we have to combine with this 1000 ohm resistor times 4 amps, which is going to be 4000 volts. So yeah, this 2 volt is kind of almost, you could almost ignore it, but I'm going to include it just for accuracy. And so then we have these 2 equations. Two unknowns. And I'm going to recommend that we just solve this using a calculator. You could again do, solve for I2 or solve for I1 and this and substitute into the other equation. There's nothing wrong with doing that, but I'm just going to turn to a calculator. So when I solved this system of equations, go away text, I got that I1 was equal to 1.999 amps and that I2 was equal to 2.665 amps. So I'm just going to round I1 to 2 amps. And the reason I'm going to go ahead and round that is obviously we've already done an approximation for the 667 ohms, because it technically should be 666.666 going on forever, but we should all know from reality and even from some of the lab work you've probably done at this point, resistors are never actually the resistor values they claim. I should be careful of that. You can get resistor with extremely high tolerances of like 0.001%, but you pay a lot of money for that. But instead what you can do here, of course, is think about the fact that, well, yeah, a 667 ohm resistor, it's going to have tolerance anyway. So I'm just going to again approximate that as 2 amps, and then we need to know what the power across my load is, which, remember, for resistors you can do I squared times R, and it's the current going through the load, and the current going through the load is of course I1, so we have 2 squared times my load resistor, which is 667 ohms, which if we do that computation, we would get 2.668 kilowatts. And of course you could run that to 2.67 or 2.7 even, but we get 2.668 kilowatts of power being dropped across that. So there's really two parts to this question. Just kind of scrolling all the way back here to this question here. Part A was to find RL for maximum power transfer, and then what is the maximum power delivered to RL. So whenever you're asked to say what is the maximum power delivered, you're going to have to do a circuit analysis, and you're going to have to decide what's the best circuit analysis technique to use. Whether you should use nodal or loop or mesh analysis. We did mesh/loop analysis for this one, obviously. Alright, so this is the end of our maximum power transfer, and just want to remind you, at the end of the previous video we talked about the fact that often we don't get to decide what the load resistance is. We often have to design our circuit so that it has an equivalent resistance equal to the load that we're attaching it to. So we'll talk more about that as well in some future videos.